Excellent. Okay, so yeah, let's dive right in. A little bit about myself, why I think I should talk about this stuff and talk to you about this stuff. I mean, I guess you're all interested since you all read this book and are fascinated by machine learning, statistical learning, and so on, as am I. So during my studies, I did a lot of statistics. So my background is actually in causal inference from observational data. And as we will see later, linear regression is kind of a very, very important topic, as Emil already mentioned also on Twitter. And I think it is very useful for you to understand the basics and the applications. We will see some applications because linear regression is used basically in a lot of scenarios, and so I think it will be useful for you guys if you understand the theory behind it, and you've already understood a lot. By the way, I mean, I don't know if that is policy, but you can ask me also questions during the talk. I don't have a problem with that, but if Emil says it's better to have it at the end. I don't have the experience that he has, so but yeah, maybe keep your questions until the end and then ask them. But I would like and I would enjoy interaction. So okay, let's start. So what is the setting, right? So basically, in statistical machine learning, you have two broad classes. One is, of course, supervised learning. I guess you're all familiar with this terminology now. And the other is unsupervised learning. So think about it for a second. What do we have in supervised learning? We have as input some data that lives in the real space, right? So n observations of p variables or in p dimensions, right? And as output, we have some y, mostly a single number that also lives in the real numbers. So yeah, and we assume that there is an unknown functional relationship between x and y. So here you see the relationship. So we assume that there is some unknown functional relationship, and this epsilon that you've just seen is included in if you do sort of statistical machine learning, then you include this epsilon, and if you're a machine learner, you might find this new to you, but you know, statisticians always use this epsilon to signify the random error term that they include. And our goal for linear regression is to find a function which approximates this unknown function for a given for a given input in some optimal way. Yeah, so there you can already see that optimization plays into that. And now it's very easy. I just want to mention that for the sake of completeness, that we can make the following distinction. If y is on a ratio scale, then or interval scale, then we call it regression. And as you've also probably already learned by now, if y is on a nominal or ordinal scale, we just call it classification. So these are the two broad under concepts in supervised learning. You have either regression or classification. And an example for regression would be, as we will see also later, for example, if you want to predict your salary based on your seniority, basically your job experience and your years of education, as a very simple example, that is an example of regression. And classification, of course, there are the very well-known and very often discussed examples of picture classification. So, for example, you have cat on a picture, and the algorithm should predict that it's a cat. That is a classic example of classification. I should mention that there is no clear separation between regression and classification. There are also regression models for nominal or ordinal variables. These regression models can be used for classification. For example, a big misnomer in this regard, if you think about logistic regression, which can also be used for classification. I know it's a little bit a head turner, but please keep that in mind. Okay, and then of course we have, I just want to mention that for completeness, we have unsupervised learning. We have as an input some data, right? But the output is unknown. And our goal then is to learn basically the data distribution, to find some patterns, to do clustering, basically find subgroups or clusters in the data. Yeah, this, for example, then has applications in marketing, if you think about targeted marketing and so on. Or we might be interested in doing dimension reduction, which can be very important if you have high-dimensional data, right? So you want to transform the data into a lower dimensional space. There have also been talks here on Machine Learning Tokyo. If you go to the YouTube side, you can see them. Very nice talks, and in which a major part of the information is included, right? There is also no clear separation between dimension reduction and clustering. Yeah, on the one hand, dimension reduction can make it easier to find subgroups in data. On the other hand, finding clusters can be regarded as a form of dimension reduction. So now let's look at the setup. As I said, we have some arbitrary inputs and nice, we call them also predictors, x1 to xn, and we have some output, y1 to yn. And we assume this relationship, this functional relationship here. By the way, the parameters, you might be familiar if you've consulted some statistics textbooks. This beta notation is very, very heavily used. These are just the parameters that you're trying to estimate. And of course, using a vector or matrix notation, we can write the linear model in this form with the definitions given here below. So don't get intimidated by this notation. It's just basically that y is some sort of number here, right? And x, we have our predictors. The betas are the parameters that need to be estimated, and the epsilon is the random error noise. And just to, I think it's always better to have it in pictures, right? So this may have looked kind of mathematical and intimidating, but think of it just like that, like this here. So we have a scatter plot, right? And we have some independent variable that we call x, right? And some dependent variable that we call y. So by the way, I try to use, there are synonyms for these terms. And the goal is that you have heard all of them, so don't get confused if I use more than one term for these. They sometimes, depending on the field also, they have different terms. I try to include every one of them so that you get familiar with it, right? And then you have this nice scatter plot here, and you can already see, right? So we could think about it, and we could assume that there is some sort of linear relationship, and we might think about how to fit, right? How to fit this line, how to predict from our independent variable the dependent variable, and we could use some sort of lineal to draw a straight line here. That would already be a good approximation, but since we are nice mathematicians, we try to have some sort of optimization that we will see later to do this for us. So with this, so linear regression has some classical assumptions that I want to briefly mention that should not be violated. So we assume that the variance of y is independent of x and constant. So basically, you can see that in this formula here. And the pairs, although the pairs are independent, so we don't have repeated measurements or time series in our data. And for estimator construction, we additionally assume stochastically independent errors. And for confidence interval in tests, we typically assume that this random error noise epsilon comes from a normal distribution with mean 1. So how can we optimally produce this line that we have drawn through the data? Of course, there comes the so-called least squares estimator into play, and the least squares estimator just says sum up all of the, sorry for the term that I don't have defined, but I will do it in a second. Sum up the residuals. Do a subtraction from the measured value, square it, and minimize the whole thing. The residual is just, if you think about it, the difference between your data point and the imagined line. Of course, in matrix notation, then this optimization problem looks like this. And if the assumptions 1 to 3 that I mentioned before hold, then we call this the best linear unbiased estimator, has a nice abbreviation called BLUE. And if we additionally assume 4, then the least squares estimator is also identical to the maximum likelihood estimator. So I've brought an example where you can see this used. As I've said, it's heavily used in a lot of empirical, basically all of empirical disciplines. Also nicely if you want to do causal inference in economics. We will come to that later. So we consider the following examples, right? We have a weight loss in milligrams of 9 batches of 25 tribolium beetles after 6 days of starvation at 9 different humidities. And here below you can see the R code that I used to generate the following plot. So on the x-axis you can see the percentage of relative humidity, and on the y-axis you can see the weight loss in milligrams. And here you can see a scatter plot of the data. And if you look at this plot, we could already assume that there is some sort of linear relationship. So we could assume that we could draw a straight line through the plot and have a relatively good function to predict weight loss from the percentage of relative humidity. Now let's do this in R. First, we compute the correlation. The correlation, as was also discussed on Slack, is basically you can measure how well the two variables correlate. And here we have a strong negative correlation of minus 0.9. This is just for the statisticians among you, that you can also perform hypothesis tests with this for the correlation. And as we've already seen in the picture, the result indicates a nearly perfect linear relationship. And now we want to determine the respective linear function. That is the following linear model. We have weight loss shall be equal to this beta 0, the intercept, plus the percent relative humidity times this beta 1. Now we can do this in R very easily, actually. We just use this call to LM, which is the linear model, and we have, this is our Y, weight shall be explained by humidity. And if we call the fit already, you can already see that R has now used the least squares regression model, has optimized it for us, and has come up with the estimate for the intercept here and the estimate for the humidity here. We can also do some, this is again for the statisticians among you, we can do a so-called summary of the fit. Then we can also see the residuals. We can again see the estimate for the beta 0 and the beta 1 here. And we have also performed some significance tests here, so we can see which variable is statistically significant. We have the adjusted R squared here. The adjusted R squared basically gives us the amount of variance that is explained by our model. Then we can use the scatterplot with or can produce the scatterplot with a regression line by calling this upline function and fit. And there we can see now we have a linear function here fitted that predicts, if we use the % relative humidity, that predicts our weight loss. So for example, if I go to 20% relative humidity, right? I can go to the line and predict that we have 7.6 milligrams of weight loss, according to our model. Okay, in some situations, you might already have thought about this. Why do we always use linear functions or linear models? There might, of course, be situations where you where a linear model might not be the optimal solution. For example, if you think about some physics models that might have an exponential relationship underlying, or some sort of polynomial model underlying, you might talk to the domain expert, and he might tell you that, okay, this is always modeled in this way and so on, and there is some good maybe physical reasons for why we would use a certain function. And this can also be done, be fitted by linear regressions, but we have to sometimes transform the original variables. Also, this can be used if the assumptions such as non-normality and heteroscedasticity. So this is actually a big term. Don't get confused by it. It just means that you have that the variance is always the same. So you don't have, like, for example, at an x value of 1, you have the same variance as you have the variance at the x value of 100. This we call then formally a heteroscedasticity, and this is also assumed in linear regression and can't be violated. But we can compensate it by transforming the original variables. I also brought an example such that you can see this. So this is the second example. So we want to predict the volume in cubic feet of trees using only the diameter, the diameter in inches of the tree. And these data come from Bruce and Schumacher. And we can look at the data in the following scatterplot. If you want to reproduce this, you can just use this R code here. So here we see it. We have on the x-axis, we have the diameter in inches, and on the y-axis, we have the volume in cubic feet. And if you look closely at the scatter plot, you can already see that this basically looks like some sort of polynomial fit. Maybe a quadratic fit would be nice here, right? Or we could also imagine, if you look at the data here, that we might also use an exponential model, an exponential function, to describe this relationship. So, as I said, there seems to be a polynomial or even exponential relationship. And first, we use the following polynomial model, a quadratic model to be specific. So we assume that the volume can be described by beta 0 plus beta 1 times the diameter plus beta 2 times the diameter squared plus our random error noise epsilon. And now we compute the linear least squares estimator and the respective tests. Again, just doing this linear model in R, the same code basically as before. I should mention, if you want to fit a polynomial model to the data, you always have to use this I, otherwise R will not understand that it's a quadratic model. So please, also if you use another polynomial, so always please use this I in front of it. And then we can see here, okay, the intercept was estimated, the diameter in the linear term was estimated, and the diameter in the squared term was estimated. We see that it's statistically significant, and we already have a nice adjusted R squared of 0.97. And so let's look at the data with a fitted line to the data. And now here you can see it that it looks kind of nice. So yeah, the data is kind of well approximated with this cubic fit. Sorry, with this quadratic fit. And again, as in the situation before, we might be very well, or we might be very good at predicting volume from diameter. For example, if we look at a diameter of 10 inches, let me just go to the fit and then to the y-axis. So yeah, we might predict a volume of 20 cubic feet. Yeah. So, but let's also try the exponential model, as we have seen this with our own eyes, and thought it might be a good idea to use an exponential model here. So this should be our model. Here you can see that it's an exponential model, and we translate that to a linear model by just using the Euler logarithm of all the variables. And then we have the following identification. So beta 0 is this Euler logarithm of A0, and beta 1 is this Euler logarithm of A1, and epsilon is this Euler logarithm of the delta. And then we can again compute the least squares estimator and the respective tests, and you can see that basically here. And we see, sorry, that an intercept is fitted, and that and we have an estimate here for the logarithm of this diameter. And what's nice here, if you look at the adjusted R squared, we can see that the R squared is even higher in the case of the polynomial model, sorry. So we add the fitted line to the data, and we look at this, and there you can see the scatter plot. We can see in blue is the polynomial model, and in red is the exponential model. And as we've seen from the R square, overall the exponential model provides the better solution. So there you can see that you are not restricted to linear functions in linear regression. You can also fit other functional relationships. You can think of also a very, very complex polynomial model. Yeah. As an example 3, this is just a literature example. I'm pretty sure some of you, or most of you probably, if not, you should do it, have read James et al., the Introduction to Statistical Learning. There I found this nice example, which is probably a little bit more of interesting for some people than these pure examples from basically ecology or science. So let's assume that we want to predict our income, right? And as predictors, we use the years of education and our seniority, right? So you can also use a regression model to do this. And as you've seen, or as you can see here, instead of a line as our graphical output of our regression, in this case, we get a plane. Okay, so this is the plane. So we have this thing in 3 dimensions, and you can see the data points and these black lines that go down to the plane. These are the residuals. And remember, in our model, we have minimized the squares of these, precisely the squares of these residuals. So again, I think as it is more Yeah, interesting for some people. Let's just go down. Okay, now this axis doesn't have numbers, but let's just assume here would be let's say let's say it's 20 years of education here or here maybe, and your level of seniority is like I don't know, 3 years. Then we go here, and then we have to go up to the plane. Now you have to think in three dimensions. It's possible. So I reach the plane now. And now I go to the income level here, and let's assume here would be, I don't know, 45,000 euros or dollars or whatever, or Japanese yen. I'm not sure what kind of currency you have in Japan, but yeah, insert your currency here, and then you can predict your income. Okay, that's it from my side. Thank you for the attention.